Okay, let's dive in. Today we're taking a deep look at something powering the engine room of high-performance computing.
Mm.
Based on the source material you've shared with us, we're unpacking a really fundamental piece of hardware for moving data around at speed.
That's right. We're focusing on the AMD Q-based Direct Memory Access, or QDMA, subsystem for PCI Express.
QDMA, right?
Yeah. The material you've provided gives us a pretty detailed view into its architecture and, how it manages that vital task of data transfer in demanding environments like data centers and telecom infrastructure.
Think of this deep dive as getting the inside scoop on a super efficient data mover. We're going to figure out what makes it different, how it's structured internally, and how it keeps massive data flows, organized and performant.
Right. And it's all based purely on what you've given us.
Exactly.
Our goal is to guide you through the core concepts and operational mechanics of the QDMA, highlighting the clever engineering and the practical implications revealed in your sources. Ready?
Absolutely. So let's start with the big picture. The sources talk about a key innovation. What is it that really sets this QDMA apart from, well, older ways of doing things?
The core difference highlighted in the material is a shift from static, fixed channels for data transfer to a much more dynamic concept based on multiple queues.
Queues.
This queue-based approach is really presented as the foundation for its enhanced flexibility and performance.
Ah, queues.
Yeah.
Where does that idea come from in this context? Is it borrowed from somewhere?
Well, the concept has roots in queue-set principles. You often see these in high-performance computing interconnects, like those used for remote direct memory access, RDMA.
Ah, RDMA. Okay.
Yeah. The design here is built with efficient, low-overhead data handling in mind, which is, perfect for today's data-intensive workloads.
And the flexibility, I'm guessing, comes from how these queues can be configured, like individually.
Precisely. Your source really emphasizes the granular per-queue configuration options. You can mix and match, choosing memory-mapped or MMDMA.
Right, like specific memory spot.
Exactly. Or AXI4 stream DMA, which is more about that continuous flow of data.
Okay.
You can pick interrupt or polling modes for completions, customize how the transfer instructions, the descriptors are set up. This fine-grained control with low overhead for setting things up or updating them on the fly, that's a key capability.
And this queue-based system allows for more complex overall setups, maybe virtualization.
Yes, definitely. The ability to assign queues to multiple PCIe physical functions, PFs, and virtual functions, VFs, is a big deal.
PFs and VFs, okay.
Yeah, PFs are the full-featured endpoints on the PCIe device, while VFs are like lightweight versions for direct assignment to virtual machines or specific applications.
Right.
This means a single QDMA core can effectively serve multiple virtualized applications or different functions within a complex system, simultaneously.
So it's much more flexible than the old way.
It's a significant departure from older channel-based DMAs and crucial for modern virtualized environments. It enables much more agile resource management.
So if I'm boiling this down, the QDMA is designed for speed, handling lots of data and transactions, sure, but the real differentiator is the flexibility it gets from this queue concept and the ability to configure each queue independently.
That's a good way to put it, yeah. The customization isn't just a list of features, it's fundamental. It's how the hardware can be precisely tuned for different types of data, whether it's large blocks in memory or continuous streams and different ways of operating.
Optimizing performance across a wide range of contexts.
Exactly.
Okay, now that we understand why it's built around queues, how is this thing actually put together physically? The source mentions a modular design.
Right. At its core, the QDMA is built around an AMD UltraScale plus PCIe integrated block that's configured to act as the endpoint on the PCIe bus.
The endpoint, okay.
And this is coupled with a lot of specialized logic for the DMA functions and also for bridge functions.
It sounds like they broke it down into specific functional units. You mentioned modular, like a team of specialists.
Yeah, exactly. A modular and pipeline structure is emphasized. Think of it like this. They designed specialized blocks to handle specific parts of the data transfer process in parallel.
To avoid bottlenecks.
Precisely, and maximize bandwidth. Key components include the Descriptor engine, that's like the command center managing the transfer instructions.
Got it.
Then you have dedicated DMA engines for moving the actual data, specific ones for host-to-card streams, H2C memory mapped, card-to-host, C2H memory mapped, and C2H streams.
4 different engines.
Yep. And interestingly, the C2H stream engine specifically calls out having a prefetch engine and cache.
Prefetching. Interesting. What else is in that team?
You also have a completion engine, CMPT. Its job is telling the host system when a transfer is finished.
Notification.
Right. An IRQ module handles interrupts. There's infrastructure for configuration management and control registers to set everything up. And importantly, bridge interfaces using AXIM and AXI Lite.
And those bypass the main DMA.
Yes, they provide direct access paths that bypass the main DMA engines entirely.
And this design with separate specialized engines that helps with performance, parallelism.
Absolutely. Having dedicated engines for host-to-card versus card-to-host and for memory-mapped versus streaming transfers allows them to process these very different types of data movement simultaneously.
And with specialized logic optimized for each.
Exactly. This parallelism is key to achieving high bandwidth.
And there's a distinction between how you control the system versus how the data moves. Control path versus data path.
Yes, that's a common and important principle in high-performance hardware. Control registers and config blocks, usually accessed via the simpler, lower bandwidth AXI Lite interface, handle the management tasks.
Okay.
The heavy lifting of high-speed data movement is handled by the specialized DMA and Descriptor engines using the higher bandwidth AXIM and AXI stream interfaces.
So the control path doesn't slow down the data path.
Right. That separation prevents the relatively slower control path from ever bottlenecking the really fast data path.
How does it connect to the rest of the system, both off-chip like PCIe and on-chip, to user logic?
It connects to the PCIe block using standard interfaces for sending and receiving transactions, the requester and completion interfaces.
Standard stuff.
Yeah. On the FPGA fabric side, it connects to the user's custom logic using various AXI interfaces. The H2C AXI-ST, C2H AXI-ST, and CMPT AXI-ST interfaces are typically set up as slaves.
Meaning user logic writes to them.
Correct. And the H2C AXI-MM and C2H AXI-MM interfaces are typically masters, meaning they initiate memory transactions to user logic's memory spaces.
Okay, so we have this modular structure with specialized blocks. Let's zoom in on what you call the command center, the descriptor engine. The source calls it the central orchestrator. What exactly does it do?
Its main job is fetching and managing the descriptors. Those are the instructions telling the DMA engines what data to move, where from, where to.
The what, where, when.
Kind of, yeah. It handles these instructions for both host-to-card and card-to-host transfers. And it can operate in one of two main modes, internal or descriptor bypass.
And it keeps track of all this for every single queue. That sounds complex.
Yes, meticulously. It manages per queue contexts. These are basically small blocks of information storing everything the engine needs for a specific queue.
Mike.
Things like the software's producer and consumer pointers, PIDX and CIDX-based addresses for the descriptor ring in memory, and configuration settings for that queue.
Okay.
It uses a round-robin algorithm to ensure fairness across all the active queues it's managing, and importantly, it reorders completions that might arrive out of order on the PCIe bus.
To maintain data integrity. Makes sense.
Exactly.
How does the software on the host tell the QDMA, hey, I have new descriptors ready for you?
The software driver writes its PIDX value, its producer index, showing where it's written new descriptors to a specific register within the QDMA.
Okay, right, the pointer.
Essentially, yeah. The hardware then tells the software when it's consumed those descriptors by writing an updated CIDX value the consumer index into a status descriptor that the software can read.
So it's a handshake using these pointers.
A hardware-software handshake, exactly.
You mentioned two modes. What's internal mode? Sounds straightforward.
In internal mode, the QDMA is largely self-sufficient. It fetches the descriptors directly from host memory and feeds them straight to the appropriate DMA engine.
Simple.
Yeah, this mode is simpler. It doesn't require any external user logic on the FPGA to handle the descriptors. Great for straightforward, standard DMA tasks.
And descriptor bypass mode. That sounds less straightforward.
Here's where it gets really interesting. Bypass mode offers a significant level of flexibility, and you can enable it on a per-queue basis.
Per queue, okay.
In this mode, instead of the descriptor engine feeding instructions directly to the DMA engine, it sends the fetched descriptors out to a dedicated bypass output interface.
And that go to?
That interface is connected to user logic in the FPGA fabric.
Ah, so the user's custom logic gets to see and process the descriptors.
Precisely. User logic can take these descriptors, pre-process them, maybe store them temporarily, or even handle custom descriptor formats initially. Then the user logic injects the descriptors back into the QDMA core using a dedicated input interface, making sure they're in the QDMA's expected format for the DMA engines to actually use.
What's the benefit of that? Why would you want user logic in the middle of descriptor processing? Sounds like extra steps.
It opens up a lot of advanced possibilities. For example, the source mentions that in H2C memory-mapped transfers using bypass mode, user logic can even interleave control commands with the DMA operations.
Oh, interesting.
And user logic also gets control over when and how status descriptors are generated. This allows for much more tailored completion signaling beyond the standard methods. It gives the user logic a lot more control over the flow of data and commands associated with specific queues.
How does it prevent things like buffer overflows when user logic is involved like that? Flow control.
Yes, it uses a credit-based flow control mechanism. You can enable throttling credit on a per-queue basis. The descriptor engine will only fetch up to the number of credits available. User logic is responsible for returning credits via a specific interface, the DSVSHI or GE interface, when it's ready for more descriptors.
So it throttles itself based on user logic readiness.
Exactly. It prevents the QDMA from overwhelming the user logic's buffers and helps maintain data integrity.
It sounds like the descriptor engine is crucial then for both handling standard, efficient transfers automatically and enabling deep customization when needed via this bypass mode.
That hybrid design is definitely a key strength of this subsystem. It enables versatility, from simple data pushes and pulls to much more complex traffic management scenarios requiring user logic intervention.
Okay, so the descriptor engine sets everything up and orchestrates. Now let's talk about the muscle, the engines that actually move the data. The source describes 4 specialized ones. Why have so many? Why not just one big engine?
Well, that specialization is a conscious design choice. It allows each engine to be highly optimized for a specific direction, host to card versus card to host, and a specific data pattern memory mapped versus AXI stream.
So specialization equals performance.
Pretty much.
Yeah.
This ensures you get maximum performance regardless of the type of data transfer you need to do.
Tell us about the H2C engine first, host to card memory mapped.
Right. This one moves data from host memory to a specific memory location on the card side. It uses the H2C AXI interface to talk to user logic's memory space.
Okay.
It handles the low-level PCIe details, like taking a descriptor and breaking it down into PCIe read requests. It has to adhere to limits like the maximum read request size, MRS, and 4 KB address boundaries specified by PCI.
The standard PCI stuff. Yep.
On the card side, it generates AXI writes. It also deals with potentially tricky issues like unaligned host memory addresses.
Ah, alignment, always fun.
Indeed. It handles them by shifting data and potentially splitting AXI writes to make sure everything lands correctly.
And the C2H engine does the reverse, card-to-host memory map.
Exactly. It moves data from the card's memory via the C2H AXI interface back to specific locations in host memory.
Okay.
It generates AXI read requests from the card side and PCIe write requests to the host. Similar to the H2C engine, it handles unaligned addresses on the host side and splits the PCIe writes to comply with PCIe rules like maximum payload size, MPS, and those 4 KB boundaries.
Right.
The source also mentions it supports multifunction virtualization. It provides the function number, the PF or VFID that the data belongs to, which is important in virtualized setups.
Good point. What about the streaming engines? H2C stream, host to card.
The H2C stream engine moves continuous streaming data from the host to user logic on the card side using the H2C AXIST interface. It parses the descriptors, issues PCIe read requests, again, splitting based on MRS. And here's a crucial performance feature mentioned. It can manage up to 256 outstanding read requests simultaneously.
Wow, 256. That's a lot.
It is. This is a key technique to hide host read latency, keep the data flowing, even if the host memory is a bit slow to respond.
Makes sense.
It also includes a 32 KB reordering buffer on the card side. This ensures that the PCIe packets, the TLPs, are delivered to user logic in the correct in-order sequence, even if they arrive out of order from the host across the PCIe fabric.
That reordering buffer sounds really important for maintaining data integrity for streaming applications. And the C2H stream, card to host.
This engine receives streaming data from user logic via the C2H AXI-ST interface and writes it to host memory. It has a descriptor prefetch cache, PFCH, which is quite clever.
The prefetch cache.
Yeah. It proactively fetches descriptors for C2H stream queues to minimize latency and prevent the engine from stalling while waiting for instructions. It even offers opportunistic prefetching based on available bandwidth.
So it tries to guess what's needed next.
Essentially, yeah, to keep things smooth. The source also mentions it can scatter a single incoming packet across up to 7 different descriptors in host memory.
Scatter-gather capability. Useful. The source mentioned different modes for that C2H stream prefetch cache.
Yes, there are several options depending on how much control the user logic needs. Simple bypass mode means user logic handles the descriptor receipt and ordering entirely itself.
Okay, fully manual.
Then there's internal cache mode. Here, the engine itself tracks descriptors, manages flow control credits using the cache, and uses that opportunistic prefetching.
More automated.
Right. And finally, cached bypass mode is a hybrid. Descriptors are bypassed to user logic first.
So user logic sees them.
Exactly. Allows user logic to process or reformat them, but then they are returned to the QDMA engine for its internal management and prefetching using the cache.
Best of both worlds, potentially.
It highlights again how user logic can take an active role, especially in these bypass modes, maybe to implement custom protocols or formats.
It really sounds like these engines are not just about raw speed, but also contain sophisticated features to handle the realities of system interaction, things like latency and ordering.
Absolutely. Features like the H2C stream's ability to manage many outstanding requests and that reordering buffer, and the C2H stream's prefetching mechanisms. These are specific latency hiding and efficiency techniques detailed right there in the source material. There's even a throttling register mentioned, H2CRQ throat, which can be configured to prevent the host-to-card traffic from negatively impacting the card-to-host performance.
So system-level awareness. Balancing resource.
Exactly. It shows they thought about the whole system, not just individual transfers.
So the data has been moved by these workhorse engines. How does the host system actually get notified that the transfer is complete? You mentioned the completion engine earlier. That's its job, right?
That's exactly right. The completion engine, or CMPT, is crucial. Its job is writing completion information back to specific memory areas in the host called completion queues, or CMPT rings.
CMPT rings, okay.
The QDMA acts as the producer, writing entries to these rings, and the host software driver acts as the consumer, reading them.
Why is this completion information so important for the host? Just knowing it's done.
It's vital for the host driver to know that a transfer has finished and, crucially, how much data was transferred.
Ah, the byte count.
Right. This allows the driver to efficiently reclaim the descriptors that were used for that transfer and free up the associated memory buffers in host memory.
Makes sense. Prevents leaks.
Exactly. Without this, you could end up with memory leaks and inefficient resource utilization. For C2H stream transfers, one completion entry typically signifies that one full packet has been received and written to host memory.
So the software knows it can process that packet and reuse the descriptor.
Precisely.
Can the completion engine send more than just a simple done signal, maybe some status?
Yes, it can. It supports sending immediate data along with the completion information directly into the completion ring.
Immediate data, like...
This could be used for out-of-band signaling or sending custom messages between the card and the host without needing a separate mechanism. The source explicitly guarantees that this immediate data associated with a C2H stream packet won't bypass the packet data itself.
Important for ordering.
Yeah.
Data arrives before its status.
Exactly. Ensures ordering between the data and its associated status or message.
How does the completion engine keep track of all these different completion rings, presumably one for each queue?
Just like the descriptor engine, it maintains a completion context for each queue.
Another context block.
Yep. This context is programmed by the host driver and stores things like the base address of the completion ring in host memory, the hardware's index into the ring, hardware PIDX, the software's index, software CIDX, and configuration details for that specific queue's completions.
Okay.
What's particularly clever here and highlighted in the source is how it optimizes PCIe traffic. It has a cache that can hold up to 64 completion entries.
A completion cache.
Yeah. Instead of sending potentially many small completion writes over PCIe, which is inefficient.
Lots of overhead.
Right. It can coalesce multiple smaller writes into larger, more efficient 64-byte writes. This significantly improves PCIe bandwidth utilization by reducing that transaction overhead.
Smart. And can the host software control when it gets bothered by these completions, like not get interrupted for every single tiny transfer?
Yes, absolutely. This is a key flexibility feature mentioned. On a per-queue basis, you can configure the notification method for completions.
Okay.
You can choose to generate interrupts, rely on status updates that the driver pulls, or use both. The driver detects new entries in the ring by checking a color bit.
A color bit.
Yeah, it's a bit that flips when the ring buffer wraps around. Or the driver can compare its software CIDX against the hardware PIDX stored in a status descriptor read from the device.
Tell us about those interrupt and moderation modes. That sounds like a way to tune CPU load, which can be a big issue with high-speed I/O.
That's precisely what it is, and the source details this as a significant strength. It allows the software to fine-tune the frequency of interrupts generated by completions, which can dramatically reduce the CPU overhead on the host, especially under high data rates.
What are the modes?
The modes listed are quite comprehensive. Trigger every. Lowest latency, interrupt on every single unread completion entry.
Like be noisy.
Can be, yeah. Trigger user. The user application or driver explicitly triggers interrupts when needed. Trigger user count. Triggers an interrupt on a user signal or when a program threshold of unread entries is reached.
Batching based on count.
Right. Trigger user timer. Triggers on a user signal or when a hardware timer expires. Trigger user timer count. This is the most flexible triggers on a user signal, timer expiration, or the threshold count.
Covers all bases.
Pretty much. And finally, trigger dis. Interrupts are disabled entirely for this queue, requiring the driver to poll for completions.
So you've got a whole spectrum of options, from lowest latency if you need it, to lowest CPU load if you can tolerate some polling or delay. Depends on the application's need.
Exactly. And the hardware provides support for timers using specific registers like QDMA to HNT and QDM-HANT for those timer modes. The engine also includes robust error handling. If it detects issues like trying to write a completion to an invalid queue or a completion ring being full, it reports these errors to the host and often invalidates the affected queue.
Which is vital for system stability, right?
Right.
Don't want errors causing chaos.
Absolutely. Containment is key.
Okay, we've detailed the dedicated DMA path, descriptors, engines, completions. But you mentioned interfaces earlier that bypass the DMA engine completely. What are these for? Why bypass the main machinery?
These are the bridge interfaces. They provide direct pathways for the host system to access memory locations or control registers on the card, and also vice versa, card to host, without involving the main DMA engines or the descriptor engine.
Why is that useful?
It's crucial because it creates two distinct data paths. You have the high-throughput queued path for bulk DMA.
The main highway.
Right. And then you have this direct memory-mapped path, usually for control plane accesses, configuration, maybe low-latency register reads writes.
Like an access road.
Sort of, yeah. This prevents your configuration traffic from getting stuck behind massive data transfers in the DMA engine or the other way around. Keeps things responsive.
Makes sense. What kinds of bridge interfaces are available?
The source describes AXI memory-mapped and AXI4 Lite versions, supporting both master meaning initiating transactions and slave responding to transactions access.
Okay.
The AXIMM Bridge Master provides a high bandwidth path for the host to access AXIMM space on the card. It can handle up to 32 outstanding requests at a time.
32 outstanding.
PCIe bars, those base address registers that map PCIe address space to device memory, can be mapped through this bridge. And importantly, it provides information like the function ID, which PF or VF is initiating the access, and the bar ID in the AXI user bits. This lets user logic on the card identify the source of the transaction. It also handles the PCI to AXI address translation.
And the AXI Lite version.
The AXI Lite Bridge Master is a lower bandwidth version, typically used for configuration and control access from the host to the card. Simpler accesses. It supports only one outstanding request.
Okay, much simpler.
Yeah. Like the MM version, it supports bar mapping and provides source identification info in the user bits. The source mentions the expansion ROM bar, if used, can be mapped here.
And the slave interfaces for card-to-host access via the bridge.
Right. There's the AXI-MM bridge slave. This is for high bandwidth transfers from the card's user logic to host memory, bypassing the C2H DMA engines.
Okay.
It translates AXI addresses from the card to PCIe addresses for the host memory. It uses a BDF table bus device function managed by system software for this translation.
BDF table, right.
It handles splitting requests to comply with PCIe rules like MPS and 4KB boundaries, and also supports up to 32 outstanding requests. The source notes it doesn't internally support narrow burst AXI transfers, just a detail there. Address translation is configured via the AXI slave CSR interface.
And the last one, AXI Lite slave.
The AXI4 Lite Bridge Slave CSR. This one is perhaps the most critical interface for user logic on the card. This is the primary way user logic accesses the internal QDMA and bridge registers for configuration, status checks, control, etc.
So user logic talks to the QDMA through this.
Exactly. A specific address bit tells user logic whether it's trying to access QDMA registers or bridge registers. Now, QDMA registers are virtualized.
Meaning they look different to PFs versus VFs.
Correct. Their addresses can change depending on whether a PF or VF is accessing them. So user logic must provide the function ID in the AXI user bit so the hardware knows which functions virtualized registers are being targeted.
Crucial for virtualization.
Absolutely. This interface is also used for generating vendor-defined messages, VDMs, which are custom messages that can be sent over PCIe.
Providing that function ID and BRID information, even on these direct bypass interfaces, sounds like it's really important for understanding who's doing what, especially with virtualization in the mix.
It absolutely is paramount, especially in virtualized environments where you might have multiple VFs sharing the same physical hardware paths. This level of detail allows the user logic to properly attribute and potentially isolate accesses based on the originating PF or VF.
Resource isolation, multi-tenancy.
Exactly. It enables that. The explicit support for BDF table translation and using AXI4 protection fields further shows these interfaces are designed with security and resource management requirements for virtualization in mind. They're not just simple pass-throughs.
That leads nicely into the last major area the sources cover, virtualization support itself, and communication between functions. Tell us about SRIOV in this context.
Single root I/O virtualization, or SRIOV. It's described in the material as an optional but very powerful feature. It's essentially a standard mechanism.
A PCIe standard, right?
Yes, a PCIe standard feature. It allows different virtual machines or applications running on a host system to effectively bypass the virtual machine monitor, the VMM, for their high-speed data transfers.
Cut out the middleman for performance.
That's the idea.
Yeah.
It makes a single physical device appear as multiple distinct logical devices, those PFs and VFs we keep mentioning, that can be assigned directly to VMs. The goal is to get near-native I/O performance by cutting out the VMM software overhead in the data path.
So PFs manage the overall device,
Right.
and VFs are like stripped-down versions for direct I/O by VMs.
That's the general model, yeah. Physical functions are the full-featured PCIe functions. They manage the device's shared resources and handle complex configuration. Virtual functions are lightweight, designed specifically for high-speed data transfer with minimal configuration resources. They're intended for direct assignment to VMs to give them direct access to the hardware's I/O path. What's particularly interesting here based on the source is that the QDMA hardware itself specifically virtualizes certain critical data path operations for VFs.
Like what?
Things like updating the queue pointers PID XCIDX and receiving interrupts for their assigned queues.
Ah, so the VM's driver can talk almost directly to the hardware for those common tasks.
Exactly. This means a VF running in a VM can manage its own data queues and get interrupts directly from the QDMA hardware without requiring the VMM to trap or mediate every single operation.
Which cuts VMM overhead and improves I/O latency.
Significantly, especially for high packet rate workloads. Non-data path configuration, like setting up memory regions or more complex features, is still handled by the more privileged PF driver, typically running in the host's root domain or management partition.
With multiple virtual functions potentially accessing hardware directly, security must be a major consideration. How is that handled?
Absolutely, and the source emphasizes this with details on built-in security features. Configuration of per-queue contexts and sensitive device registers is strictly controlled. Only privileged PFs can do this directly.
VFs can't mess with global settings.
Right. VFs have to request these types of operations, usually through their controlling PF. Drivers are also limited. They can only update the queue pointers for the queues that have been specifically allocated to their function, PF or VF.
Okay, function-level isolation.
Yes. And furthermore, a system-level IOMMU, the input-output memory management unit, can be used. The QDMA provides an ARID, an address remapping identifier, from the queue context with each DMA request it makes. The IOMMU in the system can use this ARID to verify that the DMA request is originating from an authorized PF or VF function and is targeting an allowed memory region in the host.
Adding a hardware-enforced layer of security and isolation between different virtual functions or VMs.
Correct. It prevents a rogue or misbehaving VF from accessing memory it shouldn't.
How do these PFs and VFs communicate with each other if the VMM is largely bypassed for data? They still need to talk sometimes, right?
Hmm.
For control or setup.
They do. The source describes a mailbox mechanism specifically for this interfunction communication.
Mailbox. Okay.
This is particularly useful for VFs, which have limited config capabilities, to send requests or status updates to their controlling PFs, or even for communication between different PFs. The specific messaging API, the format of the messages used over the mailbox, that's defined by the host software driver, not the QDMA IP itself.
Giving flexibility to the software stack.
Exactly.
What does this mailbox look like architecturally?
Each function, whether it's a PF or a VF, gets a dedicated inbox and an outbox. Each of these mailboxes, according to the source, can hold up to 128 bytes of data.
Okay, small message buffers.
Yeah. A VF can access its own inbox and outbox. A PF can access its own mailboxes and the mailboxes of any VFs associated with it.
So the PF can see messages from its VFs.
Mm.
How would a VF typically send a message to its PF using this mailbox? What's the flow?
According to the source material, the VF driver first checks that its outgoing message status register is clear, meaning the previous message was picked up.
Okay.
Then it writes the message data into its outgoing message registers within the mailbox space. Finally, it issues a send command to the hardware.
Telling the hardware message ready.
Right. The QDMA mailbox hardware then notifies the target PF driver that there's an incoming message, usually by setting a bit in the PF's incoming message status register.
How does the PF know?
The PF driver, which is either polling that status register or gets an interrupt, sees the notification. It reads the message, identifies the sender VF using a curse key field provided by the hardware.
So it knows which VF sent it.
Yes. And then the PF driver typically sends back an acknowledgement, often by issuing a semester SCV command specifically targeted at that source, VF. This tells the mailbox hardware to clear the VF's outgoing message status, signaling that the message was received and the VF can send its next one.
Okay, that makes sense. Handshake complete. And PF to VF communication. Similar.
Similar structure. A PF initiates communication by first setting the target function ID it wants to send to. The VF driver checks its incoming message status register and reads the message data when it arrives.
Okay.
Now, handling acknowledgements efficiently when a PF might be sending messages to many VFs simultaneously can be tricky. Polling each VF isn't great.
Right, that could be slow.
So the mailbox provides something called Acknowledged Status Registers, ASRs, for each PF. When a VF receives a message from a PF and sends its MSG-RCV command back to the hardware, this action not only clears the VF's incoming status, but also sets a corresponding bit in that specific PF's ASR.
So the PF has a dedicated place to check for ACKs from VS.
Exactly. The PF can pull an aggregate ACK status field to quickly see if any VFs have sent acknowledgements, and then read the specific ASRs to see which ones. It's a more efficient way to track acknowledgements from multiple targets.
Can the mailbox trigger interrupts instead of just requiring the PF or VF to constantly pull those status registers?
Yes, the source says it absolutely supports interrupts as an alternative notification method. This is configurable on a per mailbox basis.
Okay.
Interrupts can be sent for pending events, like incoming messages waiting to be read, or acknowledgements received. The recommended software practice described is often to disable interrupts temporarily when processing mailbox events.
To avoid race conditions.
Probably, yes.
Yeah.
Process all pending events indicated by the status registers for that mailbox, clear them out, and then re-enable interrupts when finished.
Wow, we've really gone deep into the AMD QDMA subsystem based on the material you shared. I mean, from its core shift to queues, its modular architecture, the intelligence in the Descriptor engine and those specialized DMA engines, how completions are handled with all that flexibility, the direct bypass interfaces, and the really detailed support for virtualization via SRIOV and that mailbox mechanism.
We've seen how it's designed with modularity and parallelism to tackle complex data flows, how it offers both, autonomous operation and deep customization through modes like Descriptor bypass,
Right.
how its engines are tuned for different data types and real-world issues like latency, how the completion engine provides that fine-grained control over host notification with various moderation options.
Yeah, the trigger modes.
Exactly. How the bridge interfaces create those vital separate paths for control and data, and how SRIOV and the mailbox mechanism enable secure, high-performance system integration and communication, especially in virtualized environments.
It's definitely a deep dive into the critical plumbing for high-performance data transfer. This material really paints a picture of a piece of hardware engineered for serious speed immense flexibility, and managing the inherent complexity of modern computing architectures, especially those leaning heavily on virtualization.
It shows a clear trend towards offloading complexity and enabling higher performance and efficiency through these kinds of hardware-assisted features, like the virtualization support and the dedicated interfunction communication mechanisms. Less burden on the software.
So what does all this mean for you, the listener? Well, understanding components like the QDMA helps clarify how modern hardware efficiently tackles moving truly massive amounts of data, and how it supports complex software environments running multiple workloads side by side. It's a fundamental building block that explains a lot about the performance capabilities we see in today's demanding applications.
It definitely underscores the level of sophisticated design required for hardware to achieve optimal performance and precise resource management in areas like large-scale data centers, network infrastructure, telecommunications, places where every millisecond and every byte transferred really has a direct impact.
So here's a final thought for you to consider as you mull over what we've discussed today. Given the level of built-in hardware support we saw for things like SRIOV virtualization, resource isolation via features like ARIDs and function IDs, and that secure identity-aware mailbox for interfunction communication even on bypass paths.
Yeah, that awareness was key.
Right. What might this focus on secure, hardware-assisted multi-tenancy imply about how future high-performance systems are being designed, especially thinking about handling potentially untrusted or strictly isolated workloads that need to share the same underlying physical hardware resources?
Something to think about for sure, where that trend is heading. We hope this deep dive into your source material on the QDMA has been a valuable and insightful journey for you.